Now, a special number that could come up from taking the scalar product is 0. So 0 has a geometrical significance here. If your scalar product is 0, let's take the geometric version of the scalar product, then it gives you 3 different cases. Either if the magnitude of vector A is 0, it also implies that vector A is 0. You have that if the magnitude of vector B is 0, then the vector B is itself the 0 vector, or that cos theta is 0, and cos theta is 0 only when theta is equal to pi over 2. Now, in most cases, they will tell you you're dealing with a non-zero vector. So A and B are non-zero vector, or you are actually given numbers for A and B, therefore they cannot be the 0 vector, which immediately means that if you're getting a scalar product of 0, then in most of the cases, it is that the angle is pi over 2. And when the angle is pi over 2, it means it's at a 90 degrees, which means that your 2 vectors are perpendicular, or another name we use is orthogonal. So, for example, this could be vector A, and this could be vector B, and you have this pi over 2. And if I take this scalar product, then it's going to be 0. So a couple of properties that we're going to look at with scalar product is going to help us solve different types of questions. If I take the scalar product of A times B, it's the same thing as B times A, so it is commutative. If I take the scalar product of the same vector, it's the same thing as taking its magnitude and squaring it, so this is a useful property. Another thing is I can spread out, I can distribute these, but when you distribute, you make sure that what you have in between is not a multiply, it's a dot product or a scalar product. And then same thing with a scalar. So you can distribute the scalar. Sorry, not distribute the scalar. You can take a scalar with one of the values here and then take the dot product, or the other way around, you first take A and then the scalar, the dot product with the result of the scalar and the other vector. So these are some useful properties we have here. Now, about the angles, if the vectors are collinear or parallel, then you would expect that the dot product is just going to be a plus minus of the magnitudes themselves. So it's not, you won't be faced with any angles or so. Because if they're parallel to each other, then the angle is 0, and cos of 0 is going to be 1. So that's something you would look into. If it's positive, then they're moving in the same direction. If it's negative, then you have the opposite direction. So this would be A, and you have B, and because the angle between them is 0, and you have cos of 0 is 1. But if you have the opposite direction, so this is A, this is B, then you have the angle is 180, or the angle is pi, and cos of pi is negative 1. So it's still based on the formula, it's just simplifying it for you. Now, if your scalar product is positive, then you have an acute angle, and if it's negative, then you have an obtuse angle, which is something we've seen in the last lesson. So the value you get tells you something about the vectors, whether it's plus or minus, and the positive or negative of the scalar product tells you the type of angle you have. So this is again another summary of the type of answers you could get and what they mean. So in general, the dot product giving you 0 means that they're perpendicular. This is an if and only if statement, meaning that if they're perpendicular, then this holds true. Then another thing is they would be parallel vectors. Notice how we're taking the absolute value here just to eliminate the oh, they're moving in the same direction or opposite direction. We're just concerned with them being parallel. If you remove the absolute value here and it gives you a positive answer or a negative answer, then you'll know more about the direction. And then, as we said, if it's positive, it's acute. If it's negative, it's obtuse. And the angle between two vectors is always taken as from 0 to 180 or 0 to pi. We don't consider the reflex angle. So keep that in mind. We will also use this fact later on when we deal with angles between lines and planes and so on. So we're just going to go through 2 examples to reinforce these concepts. So if I have these 2 vectors, and I would encourage you to do this question on your own first. I have these 2 vectors. I'm given the magnitude, but I'm also given that a linear combination of them are perpendicular, not A and B are perpendicular. Using this fact, I need to find the angle between vectors A and B. So quite a bit of work here that we need to do. So what I'm gonna do is actually just set up the beginning. So I know that if I need the angle between A and B, I need to take cos of A and B over the magnitude of A and B. Okay, so these are not perpendicular, so I know I can't do much, but what I do have is the magnitudes in here. Or actually, just let's us write it as cos theta is equal to that. So so I know cos theta is equal to A B over, so we have 3 times 2, so that's a 6, which means that the scalar is just 6 cos theta. So this is the theta I'm trying to find. This will give me the angle between A and B, but I don't have any other information that could help me here. I do have another piece of information about the linear combination of A and B. So I know that if I take the scalar product of this and this, it should be equal to 0 because they're perpendicular. So as soon as you see these, you can write it as a fact scalar product is 0. So I'm taking the scalar product, I'm making it 0. So what can I do now? Well, going back to the properties of scalar product, I can expand, I can distribute, and so on. So if I go A and A, remember it's not a multiply, it's a dot product, A and A. And then I have A and minus 2B. I'll take the minus 2 because it's a scalar, and then it's A dot B. And then I have the B and A, which is the same thing as, we said they're commutative, A dot B. And then I have, again, a minus 2 and then a B dot B. So I am using the properties that I showed you a few slides ago. And again, I'm going to use the properties again from a few slides, which is that if you have A dot A, it's the same thing as taking the magnitude and squaring. Same thing here. You'll get minus 2 and squaring here. And then minus 2AB plus AB, deal with it like normal algebra. This will give you A minus A dot B. If you notice now, we have a lovely A dot B here that we could substitute. So I will just take it to the other side. In here you can do the algebra in any way you'd want to. Sorry, I forgot the... Okay. So taking it to the other side, I know that it's equal to 6 cos theta. And I actually know the values of the magnitude of A and B. The magnitude of A is 3, so 3 squared is just going to be 9, and 2 times the 2 squared, that's just going to be, let me just write it there, so you have a 2 and 2 squared. So continue solving algebraically. You're trying to solve for theta here, so you end up with cos theta is equal to 1 over 6, and theta is theta is going to be 1.40. That's the 3 significant figures. So that's for this example. And here again, a different type of example that could show up. Again, I would encourage you to try it before you see my explanation. For part A, you need to find, I need a relationship between them. Well, if they're perpendicular, again, we know that the scalar product is just going to be 0, which means that if I take 2 multiplied by mu and I add to it an alpha times -5, it will give me 0. Now obviously you can rewrite this nicely. 2 mu minus 5 lambda, sorry, I meant lambda alpha, is equal to 0. So that's the relationship between them. They've set this up because it's going to be helpful for part B. In part B, I need 2 possible vectors for vector A if I know that the magnitude of B is 13. So if I know the magnitude of B is 13, let me use that fact. It means that mu squared plus a -5 squared is equal to 13. And when you try and solve that, you end up with mu is equal to a plus minus 12. You need, again, keep in mind, if you're taking a square root, consider whether you're taking the positive and negative. We've mentioned this before, where if you're dealing with magnitude, no, you just take the positive. But because I've used the magnitude to find an actual value, this value could be plus minus. So you need to take both, unless stated otherwise, obviously. So because of this, I can now go back here and see what values I could possibly get for lambda, and therefore the two possible vectors for A. So if my mu is positive 12, then going here, minus 5 lambda equals to 0. This will give you lambda to be 24 over 5. And if I take a negative 12, this will give me a lambda negative 24 over 5. So in general, vector A could possibly be 2 24 over 5, or it could be 2 negative 24 over 5. Both of these vectors satisfy the fact that they will be perpendicular to vector B, and that the magnitude of vector B is 13.